in which we studied the combined stress calculation, short prismatic member, unsymmetrical sections. So we calculated these things. Okay. Recording starts. Okay. Thank you. And our second module was related to stress and strain transformation, in which we also study some elastic constant relation between elastic constant and failure theories. Our today's lecture is about module 3, which is shear flow in beams. So in today's lecture, we'll talk about the shear stresses in beam. You studied this topic in your mechanics of solid 1, but I want to revise this as it is related to the shear flow. So after revision of this, we'll study the shear flow and shear flow in general, shear flow in thin sections, shear flow in closed sections. And at last part of this lecture, we'll talk about the shear center. Okay, so this is the outline of today's lecture. Now I'm going to start shear stress in B. You people are already aware of these things, but I want to revise this as I want to have a background for the shear flow. Okay, so I'm going to have a detail of this, detailed discussion on this. So this is a member, okay, a part of a member, a beam, a part of a beam which is subjected to some generalized loading. Okay. And there are two sections on the beam, section 1 and section 2, which are dx distance apart, differential distance apart, meaning that they are very close to each other. There, this dx approaches to 0. Okay, so they are very close to each other. Okay, so this is for clarity. I've shown its length like a finite length. Okay, so this is a differential length of the beam, and the moment, as the loading is variable along the length of the beam, so as the shear force and the bending moment will vary along the length of the beam. So let's suppose that the bending moment at this section 1 is m1 and at section 2 is m2. I've shown these both of them as a positive value, though this one is a clockwise and this is counterclockwise, but both of them are representing positive value. Okay, and why they are representing positive value? Because at section 1, if you are, according to our sign convention, if you are calculating bending moment from the left side, and all the movement which are producing a a clockwise effect are considered as positive. And if you are calculating moment from the right side, so all the movement which are producing a counterclockwise moment are considered as positive bending moment. So both of them are positive. So M1 and M2. Okay, now let's take an exaggerated view of this element, this differential element. So this is this differential element, its length is dx and the depth is equal to depth of the beam. This is not the cross section, remember. Okay, cross section of this beam, I have taken a general cross section. So this is a trapezoidal cross section. This is the cross section of this beam. If you just cut it and see it from the side, so you will see a trapezoidal shape. So it could be a rectangular shape, it could be a circular shape, it could be any other shape. Okay, it could be any other shape. So this is in general is a trapezoidal shape. Okay, so here you can see if a bending moment is applied at a certain section, so flexure stresses are produced. Okay, and the flexure formula, at if the moment value is m1, then according to the flexure formula, the stresses induced at this section 1 at any depth, if I've represented it with sigma 1, because this is at section 1, so sigma 1 is equal to m1 over I into y, where I is the moment of inertia of this cross section. जो भी इसका cross section has, so this is the moment of inertia of this whole cross section. Okay, and at this section 2, the stress is R sigma 2 is equal to minus m2 over I into y. Okay, so these are the stresses induced at section number 1 and section number 2 because of these bending moments m1 and m2 respectively. Okay, and this is the neutral axis, because In the case of pure bending, pure elastic bending, we know that the neutral axis coincides with the centroidal axis of the member. So neutral axis is known to us because centroid, we can locate centroid of any cross section. Okay, so we can locate the centroid. So this neutral axis is already known to us. It's a geometric property. This neutral axis is a geometric property. It depends upon the geometry. For rectangular section, the neutral axis passes through the centroid. For triangular section, the neutral axis is at a distance of 1/3 from base of the triangle. Okay, for circular section, it is passing through center of the section. Okay, and for semicircular section, it is at a distance of 4r divided by 3 pi from base of the circular section, from diameter of the semicircular section. Okay, so the neutral axis is known to us. So this is the stress distribution diagram. Okay, now let's take an element, the shaded element, at a distance of y. I've shown y here. So this is shaded element from the from the front, and this is the shaded element from the side. Okay, so this is, you can see the shaded element in the cross section, and here you can see the shaded element as a front view. Okay, and here you can see the three-dimensional view of this element. So this shaded portion is this one, and this shaded portion is this one. Okay, so let's take equilibrium of this small element. Okay, so this is a part of the differential element. Okay, so this is, I've shown it here separately, the shaded element. So the force is acting on this shaded element, the stress is acting on this shaded element are this one. This is will be a trapezoidal distribution. This is the stress variation here, a trapezoidal stress variation, and here is the stress variation, only the stress acting on this part. So this is these are the flexure stresses. Okay, these are the same flexure stresses acting only on this element. Okay, now if you integrate these stresses over the area, and the area, if you see this stress, so this stress is acting on this cross-sectional area, not the whole cross-section area, only this shaded area, not this area. Okay, the cross-section area, because the stress is acting on the cross-section. The stress is acting along the axis of the member, which is perpendicular to the cross-section. So you will have to integrate it on the cross-sectional area, which is this shaded area or this area. Okay, so if you integrate this stress on this shaded area, you will get the force. So F1 is sigma 1 into dA into integral. Okay, so this will give you F1, the force acting on section 1. Okay, if you plug in the value of the sigma 1, which is m1 over I into y, so you will get this expression. Since m1 over I is constant for any cross section, okay, so you can take it out from the integral and you will get this expression y dA, so which is minus m1 divided by I into q. This q is what? This is the first moment of area. And first moment of area of which area? Of this shaded area, not this one. This is not in the cross-sectional dimension. This is in the cross-sectional. Okay, so you will have to take the first moment of area of this portion. Okay, so if you can calculate this, then you can calculate the force acting on this member. Okay, and the location of the force will depend upon the area, the shape of the area, and the pattern or the stress variation. Okay, so this will give you only the force. Location of the force is not yet known to you. Okay, for some cases, if you have a rectangular variation, okay, you can get this force, but we don't need that, the location of the force. Okay, now you can calculate the first moment of area Q either as this integral, or you can calculate it as this one, A shaded into y bar. You can see this is the centroid of this shaded area. This is the neutral axis, so the distance between centroid of the shaded area and neutral axis of the cross section is y bar, and A shaded into y bar will give you the first moment of area. So it's easy for rectangular section. For many areas, the centroid is known to us, so the area is known, the centroid is known, and if you have a number of area, then you can sum them up. Okay, so this here you can say summation, but since here we have just one area, so that's why I'm not using the sign summation. But if you have a number of areas, then you can have a summation sign. Okay, so this is the first moment of area. Similarly, for section 2, you can calculate section F2 is equal to integral of sigma 2 dA. So this is M2y divided by I into dA. Take it out as a constant, so you will get this expression. Here, since this is YdA and this is also integral on the shaded area, so both the section 1 and section 2 have the same cross-section area. Okay, same cross-sectional shaded area. Okay, so that's why Q will be same for both sides. Okay, now you got the value of F1 and F2. Now, if M2 is greater than M1, here I've shown it like this is these stresses are small and these stresses are higher. So it depends. There is a possibility that M1 will be greater than M2, but I'm just interested in this. So I want to get a positive change in bending moment. So that's why I'm taking M2 as greater than M1. Okay, so dF is equal to F2 minus F1. So you will get a force here. If this is F1 and this is F2, so this element is not in equilibrium. Since this beam is in equilibrium, this portion is in equilibrium, so this portion must be in equilibrium. Okay, so F1 and F2, since they are not equal to zeros, they are not equal to each other, so there must be an equilibrium force applied at base of this element. Okay, at base of this element, which is dF, and dF is equal to F2 absolute, but because I want to get rid of this sign, so F2 absolute minus F1 absolute. So plug in the value of F2, plug in the value of M1, so you will get Q over I M2 minus M1 and M2 minus 1. Since the distance between section 1 and section 2 it is differential, so the change in bending moment will also be differential. So Q over I into dm. So this is what? This is the differential force, this dF force acting. This force, this in the three-dimensional view, this force will be acting at the base of the shaded element in this direction. Okay, parallel to this F1 and F2, but at the base of the element. Now, this is a shear force, since this is parallel to the resisting area. So if you just divide this shear force with the area on which it is acting, so you will get what? You will get shear stress. So now dF is acting on this area, one dimension B, other dimension dx, or if you say this is dx and this is B in these two views. So this dF force is acting on this area. So if you divide this dF with B dx, so you will get shear stress, and this is horizontal shear stress. This is what? This is horizontal shear stress. This stress acting in horizontal direction. So that's why the name given. TH, the horizontal shear stress is the name of horizontal shear stress is given to us. So just plug in the value of dF from this equation. So you will get Q over IB into dm by dx, dm by dx. Okay. Now dm in this case, remember that B is the width at the location where you want to calculate the shear stress. Okay, here you want to calculate the shear stress. So what is the width? Since this is a trapezoidal section, B at the top is smaller and at the bottom it is having a higher value. Okay, so you will have to have a value where of B where you want to calculate the shear stress. Okay, so Q divided by IB dm by dx. Okay, now according to definition, we know this, that the rate of change of bending moment is equal to shear force. So dm by dx is what? Is equal to the shear force. Okay, V. If you have a constant bending moment diagram, then you can see that the shear force at that location will be equal to 0. There will be no shear force acting on that segment of the member where you have a constant bending moment. But usually bending moment varies, and if there is a variation in the bending moment, there must be a shear force, and the rate of change of bending moment is equal to the shear force. So if you replace in this equation dm by dx with v, and then finally you will get this equation. So this is the equation for shear stress. Now it's very, very important to know all these four terms. Okay, to know all these four terms. V is the shear force acting at that section. Okay, let's suppose if you have the shear force is varying along the length of the beam. So if you want to calculate a shear stress at a certain location, then you will have to calculate the shear force at that section where you want to calculate the stresses. So this is the shear force. Q is the first moment of area of a portion of the cross section, not the whole cross section. Of a portion, let's suppose if you want to calculate, in this case, if you want to calculate shear stress at this location, okay, and here we have an assumption, okay, I've forgotten to have this assumption that we are assuming in this case that along the width of the beam, the shear stresses are uniform. The shear stresses are uniformly distributed. This is a big assumption, and we'll talk about this, that same shear stress is acting at this location, this location, this location, this location, this location. So the shear stresses do not vary along the or across the width of the beam. Okay, so they are uniform. So we are assuming that they are uniform. Okay, so this is the moment of inertia and width B. So B is the width of the beam where you want to calculate the stress, and Q is the first moment of area of the portion on one or other side of the cross section. Now it is important to know about the definition of Q. If you want to calculate shear stress at this location, that you will have to draw a horizontal line at that location, okay, and then calculate the first moment of area of the area on one side of that location of that section. So here this is the isolator line. So it is dividing the area into two parts. One is this unshaded portion, the other one is the shaded portion. So you will have to calculate the area on one side of this line, this isolator, okay, so this shaded portion or this unshaded portion. Remember that the first moment of area of this shaded portion will be equal to the first moment of area of this unshaded portion. Though the area of this unshaded portion is higher, but its centroidal location is smaller. Though the shaded area is smaller, but its centroidal location, its y bar is high. Okay, but both of them will result in the same value. Okay, so you will have to, if you want to calculate, let's suppose if you want to calculate shear stress here, draw a horizontal line and take the first moment of area of this or the area above that that line, okay, that horizontal line. Okay, so this is important. So V is the shear force, Q is the first moment of area, I is the moment of inertia, and B is the width at that location. Width may be variable, may be constant. In the case of a rectangular circular section, so sorry, a rectangular or square section, it is constant. But in case of a circular section, in case of a, let's suppose a T section, in case of triangular section, so B is not constant. B is variable along the depth of the beam. This variation may be continuous or this variation may be abrupt. Like in the case of T beam, there's an abrupt change. But in the case of a triangle, the variation is a uniform variation. Okay, now this tau h, if x is along axis of the member and y is along vertical direction, that is in the direction of the shear force, then the shear stress may be denoted as tau yx. Here you can see this is the horizontal shear stress. This is a stress element. This is horizontal shear stress. If this is x-axis, this is y-axis, then you can represent this tau h with this tau yx. Okay, because tau h is acting in a horizontal direction but on y plane. This is y plane. Why this is y plane? Because its perpendicular is y. So we can represent this tau h as tau yx. So tau yx, we can say that tau yx is vy into qz. This q is calculated about the neutral axis, which is along the z axis. This is IZ and BZ. B is also along the Z axis. So here you will have to take care, because the shear may be acting in a horizontal direction. Then you will have to calculate Q about Y. If V is Y, Vy, then this should be QZ, this should be IZ, this should be BZ. If this is VZ, then this should be QY, IY, BY. Okay. Now let's have a relation between horizontal and vertical shear stress. Let's have a relation. Okay, and we know that we have used it in the stress strain transformation. Okay, but we just use that and we prove that. But I want to repeat that procedure, and I want to just have this relation that this tau yx is equal to tau xy. Okay, and you can prove this. So if you have this stress element, this is a 3-dimension of the stress element, this is dx, dz, and dy. So I want to prove that this stress is equal to this stress. Tau yx is equal to tau xy. This tau xy, so this is the stress element, and these are the forces. So if you multiply the stress with the area, so if this is fxy is equal to tau xy into dy dz, because this is tau xy is acting on dy and dz. And fyx is acting on what? dz and dx. So multiply dx and dz with the tau yx. Now plug in the value of and now apply the equilibrium condition. So these two forces, this one and this one, they are creating a couple, and these two are also creating couple. So this couple is counterclockwise and this is clockwise. Since the body is in equilibrium, the stress element will be in equilibrium. So apply moment equilibrium condition, and this couple must be equal to this couple. So if you have fxy into dx plus fyx into dy, plug in the value of fxy and fyx. So you will get finally that dx, dy, dz will cancel, and you are left with tau xy is equal to tau yx. That with the shear stress. So since this is a vertical shear stress and this is horizontal shear stress, we know that this is horizontal shear stress. So the horizontal shear stress at any point is always equal to the vertical shear stress, or the horizontal shear stress in a beam is accompanied by vertical shear stress in a beam. Okay, there must be it cannot, the horizontal shear stress cannot act in isolation. It must be, this is equilibrium requirement. Okay, if the horizontal shear stresses are produced in a beam, then they must be accompanied by the vertical shear stresses. Okay, so this is important. Now coming to limitation of the shear stress formula. The limitation of the shear stress formula. So there are some limitations of the shear stress formula. Number one, the shear stress formula is based on the assumption that it is uniform across the width. The shear stresses are uniform across the width. However, in beams with flayed sections having higher width to depth ratio, like this is a cross section, this is a flat, in which the width is greater than h. Okay, the stresses are no more uniformly distribution, and the shear formula is not applicable. The shear distribution is like this. This is the shear stress distribution. Okay, this is not a uniform distribution. Okay, this is not uniform distribution. This is non-uniform distribution. Okay, so if you have a flat section and if you want the shear stress formula to that flat section, so there will be some error in your calculation. Now, how to get that error? So this is beyond your scope, but from theory of elasticity, I've reproduced some of the error, that if you have B over H equal to 0.5 and B over H equal to 2, so the error are 3% and 40%. So B over H equal to 0.5, like if you have a cross section like this, B is smaller than H, this is B and this is H. And if you have this case, like if you have BH or B over H equal to 2, so you have a flat section. So in this case, the error is very small. 3% is a negligible error. Okay, and 40% is not a negligible error. Okay, 40% is not a negligible. If let's suppose if you are calculating that shear stress produced in a beam is, let's suppose 20 psi. Okay, using this formula. Okay, so if you calculate and you are getting a 20 psi, and if the beam is flat with a B over H equal to 2, then the actual value will be 1.4 times. This is, since this is an error, so it will be 1.4 times that of 20. So that will be, so if you multiply 1.4 with 20, so that will be 28 psi. So the maximum stress which is at the end will be 28 psi, and the stress at the middle will be less than that, the value calculated. Since we are interested usually in the maximum value, so the maximum value will be 1.4 times that of the value calculated in using the shear stress formula. Okay, so in the case of routine beam, usually we have these cases that the width of the beam is greater than the depth of the beam is greater than width of the beam. Okay, usually we do have these cases. Usually we are in a ratio of B over H equal to 0.5 usually. Okay, so the error is very small. Okay, the error is very small, but if you are using formula for a flat section, then you will have to take care of this, and there are some correction factor given, so you will have to just multiply that with the correction factor, so you will get the actual value of the shear stress. This is one thing. Next is the shear formula will not give accurate result where there is an abrupt change in the cross section at the flange web junction due to the stress concentration. You have this case. You can calculate shear stress in the flange, you can calculate shear stress in the web, and there will be an abrupt change. The shear stress in the flange will be smaller, and the shear stress in the web will be very high, depending upon the ratio of the width of the flanges and the thickness of the web. If you calculate, so there will be a change, a higher change. We'll have an example on this. So if you have a abrupt change in the stresses, so that is known as a stress concentration. So there must be some more stresses due to this change. In the cross section, there is an immediate change in the cross section, so the stresses will be higher than the value you calculated from the shear stress formula. Okay, the third point is that the shear formula gives stress in vertical direction. If the boundary of a section is not vertical, not perpendicular to the neutral axis, the shear formula is not applicable. Okay, we are getting stresses in the vertical or in the horizontal direction. Horizontal is along the length of the member, and vertical is vertical. Okay, so vertical stresses, we are getting vertical stresses, but since if you have an inclined surface of the cross section, like this is a cross section, if you have an incline, then the stresses will be like an actual stresses will be in this direction, but since your formulation is giving you stresses in this direction, which will be wrong. So the formula is also not applicable to when you have some inclined surfaces. The surface is not vertical, like in the case of a triangular section. But how much will be the variation? So this is beyond your scope. You can get it from the theory of elasticity. Okay, the theory of elasticity will give you the exact variation of these shear stresses. Okay, so these are the three main limitations of the shear stress formula. Okay, three main limitation in addition to all the assumptions which were made for the flexure formula. That the material is elastic, material is homogeneous, isotropic. Okay, elastic, homogeneous, isotropic. Okay, that the main assumption is that the plane section remain planes. Okay, the beam is initially straight. Okay, the beam is not curved, the beam is initially straight. Okay, the bending moment is applied about the principal axis, so there is no chance of the unsymmetrical bending. So all those assumptions are valid, and then you can use this formula. Okay, so in addition to all those assumptions, you have some more limitation of the shear stress formula, and these are these three important limitations. Okay, now next is an example on the shear stress. So draw shear stress variation diagram across depth of the given T section as shown in the figure. The shear force at the desired section is 100 kilonewton applied along y-axis. So you have the cross section as a T section, and at a certain location, the shear force is 100 kilonewton. So he is saying that draw the shear force, the shear stress variation diagram. So since we discussed this I section so many times, so I've taken the geometric properties. So here the geometric properties needed is the moment of inertia about z-axis. So Iz is equal to 518,258 millimeter power 4. The applied shear force is in the y direction. Okay, so Vy is 100 kilonewton. Okay, to draw the shear stress variation diagram across the depth of the flange and web, consider two sections at variable distance y from the neutral axis, one in flange and other in the web as shown in the figure. Here you can see I've taken one section at a distance of y in the flange. I have taken another section at a distance of y in the web. Okay, now to calculate the shear stress, I'll have to calculate the first moment of area on one side of that section. So this is section, this is the shaded area is on one side, and in the case of this section, the shaded area is this one. On one side, you will have to take this one or this rectangle. Okay, so let's for the flange, the first moment of area, this shaded area is 50. Here, this distance is y. What is about the depth of this shaded area? 24.1 minus y. So 50 is the width, 24.1 minus y. So this is area. And what about the centroid? How to get the centroid of this? So since this is rectangle, so the centroid will be at the center of this depth. Okay, so how to get that? So it's very easy if you know bottom and if you know top. What will be about the center? It will be average of the two. So if this is y and this is 24.1, the center will be y plus 24.1 divided by 2. Yeah, 24.1 plus y divided by 2. So this is what? This is y bar. Y bar. Y bar is equal to this one. This is shaded area. So shaded area into y bar. So this will give you 250 divided by 2 is 25, and this is a minus b, a plus b. So this will give you a square minus b square. So this is the stress. This is the variation. This is an equation for the shear flow in flange. So this equation is applicable only to flange. Okay, and you will I've written it QZ because I'm calculating about the z-axis, about this axis. Okay, now the shear stress is TF, tau F is equal to, F is for flange. Okay, so Vy, QZ, IZ or B. Okay, here Vy is 100,000, QZ is this one, I is this one, and width in the flange is 50. B in the flange is 50. So if you simplify this relation, you will get this equation number 1. At top of the flange, like here, what is the value of y? 24.1. So 580.8 minus 24.1 square will give you 0. So at the top, at this location, the shear stress is 0. Okay. Now at bottom of the flange, at this location, like here, anywhere along this line. Okay. So at bottom, the shear stress is 36. If you just plug in, because the y value at here is 24.1 minus 10, which is 14.1. Okay, so 14.1 square, so you will get 36.86 MPa. So the stress value, the shear stress value at bottom of the flange is 36.86 MPa. Okay. Now coming to the web. Okay, so for the web, if you want to calculate the first moment of area, so I'm dividing it into the flange area or into the web area. The flange area is a constant area 50 into 10. and 24.1 minus 5, because your center is at this is center, so from top the centroid of this shaded portion is 24, is at a distance of 5. Okay, so this is for this rectangle, 15 to 10 into 24.1 minus 5. And for this small rectangle, so this is 10 into 14.1 minus y. This is y, so the remaining distance will be 14.1 minus y, because the top is 14.1. Okay, so this is 10 into 14.1 minus y. This is area, and its centroid is similarly y plus 14.1 divided by 2. This is bottom is at y, top is at 14.1. So mid will be at the average of these two. So 14.1 plus y divided by 2. Okay, so if you simplify this one, simplify this, so you will get 10 544 minus 5y square. So this is the first moment of area. Okay, first moment of area for a section in the web. Okay, now the shear stress in the web, V by QZ divided by RZ into B is equal to this one. So this is finally 203.45 minus 0.0965 y square. Okay, so if you use this equation to calculate, so the applicability of this is applicable from here, where the value of y is minus 45.9, to this one where the value of y is 14.1. So minus 45.9 is less than or equal to y is less than or equal to 14.1 for this equation. Okay, so a top centroid and bottom, a top centroid and bottom of the web. So this is top. Okay, so at the top the value of y is 14.1, so 184.26. At the bottom, at the centroid, y is 0, so this is 203.45, and at the bottom y is minus 45.9, so this is 0. So these are the values in the web. Okay, now if you want to calculate the maximum value, okay, in the web, so since this is a smaller value, then higher value, then decreasing, so there must be some maximum value. So from the maxima and minima, you can have it that d tau divided by dy is equal to 0. So this is, if you just integrate this equation, so this is 0 minus 0.09 into 2y, so y is equal to 0. So it means that the shear stress is maximum at the neutral axis for this case. Not for all the cases, the shear stress is not always maximum at the neutral axis, but in this particular case, the shear stress is is maximum at the neutral axis. So this is the stress variation diagram. This is not a straight line. This is a second degree curve. This is also second degree curve. So this is 38.86 in the flange, but as you are coming to the web, so you have 184.26 at the same location. This is bottom of the flange, and this is top of the web. So this is in the web and this is in the flange. Okay, so in the flange the maximum stress is 36, but at the junction the stress is 36.86, but in the web the stress at the junction is 184.26. Okay, so as you are shifting from flange to web, so there is an abrupt change in the stress, and that's what we were talking about in the case of limitations. So the stresses are abruptly changing from 36.86 to 184. Now the ratio between these two is equal to the ratio between the width of the flange and thickness of the web. So here in this case, the ratio, since this is 5, this is 10, and this is 50, so 50 divided by 10 is 5. So the ratio between this divided by this must be equal to 5. So if you divide 184.26 divided by 36.86, you will get exactly 5. Okay, so this is basically, this is equal to this change is because of the width. Okay, since the first moment of area at this location is same for both the cases, but the only thing which is variable is b. B in the flange is 50 and b in the web is what, 10. So the stress variation will be what? Stresses will vary, like the ratio between the two will be 5. Okay, because it depends upon b. Rest of the thing are same, the same shear stress, same moment of inertia, and same first moment of area. Okay, so this is the shear stress variation diagram along depth of the beam. Okay, shear stress variation diagram along depth of the beam. कोई क्वेश्चन आपकी तरफ से? Any? Okay. Now coming to now, if we know about the shear stress in beam, just give me a minute. अच्छा जी. So now coming to the concept of the shear flow. The concept of shear flow is used in the design of connection between various parts of a built-up section. Like we studied this, if this is a built-up section, like this is, if these are, let's suppose if this beam is made of wood, okay, and this is made like two planks of wood are nailed together to get this T section. So you will have to, like, this is one element and this is another element, and you will have to then connect them using some screw. What should be the size of screw and what should be the spacing between the screw? So this is what is required. Okay, and this you can do if you know the force resisted by a single screw, and this you can do using the shear flow concept. Okay, so how for a flange, if for example, if a wide flange section is made with individual plates joined together using welding or bolting riveting, the weld requirement or the number spacing of the bolt rivets can be determined using the concept of the shear flow. Okay, this is one application of the shear flow. There is another application. There is another application, and we'll talk about this one. Another application of the shear flow is the determination of shear center of unsymmetrical sections. Okay, shear center, the concept of shear center. So that's we'll talk about in last of this lecture. Okay, so this is related to, this is one application, and this is other application of the shear flow. Now, the shear flow, what is shear flow? The shear flow in beam is the shear force per unit length is against the shear stress, which is the shear force per unit area. This is what the shear flow is. What the shear flow is, force per unit length. Okay, and it is denoted by Q, and this is the same concept. You can derive with the same concept if you have this dF force, and if you, instead of dividing the force with the area, if you divide this force with just this dx, then that will give you a shear flow. If you divide this dF with the shear area, then that will give you the shear stress. But if you divide this with the length on which it is acting, so dF by dx will give you what? The shear flow. So as per definition, Q is equal to dF by dx. Plug in the value, we know that dF is equal to Q dm by I. So this is dm by dx, and dm by dx is equal to V. So we got that Q is equal to VQ by I. Okay, VQ by I. And here you can see the difference, that here in the case of a shear stress, we have VQ by IB. Okay, but here you don't have any B because it is per unit length. It has nothing to do with the width of the beam. Okay, so relation, what is the relation? Then you can see that the shear flow is VQ by I, so you can write it VQ by IB into B. Okay, you divide it and multiply with B. Since this is equal to tau, so Q is equal to tau into B. Okay, so this is a simple relation. So both of them, the shear force and the shear flow, are same quantities. The only difference is the width of the beam. So if you divide are the thickness of the beam. If you multiply the shear stress with thickness of the beam, then you will get the shear flow. Okay, shear flow. Now let's solve the same example which we solve for the case of shear stresses. So draw shear variation and shear flow variation diagram across depth of the given T section as shown in the figure. The shear force is at the desired section is 100 kilonewton applied along y-axis. Okay, so this is the shear force is acting in this direction. So what is the shear flow? So we know that we discussed it, that this is already known to us. This is the shear force, and this we already discussed this one. Okay, we discussed this one, and this is the same thing which we studied in the case of, so the definition of first moment of area is same. Okay, so QF is equal to Vy QZ divided by Iz. Plug in the value and you will get 4.824 into 580.8 minus y square. You can get at the top of the flange, you have 0. At bottom of the flange, you have 1843 Newton per millimeter. The unit of the shear flow, since this is force per unit length, so in this case, the unit is, since the linear units are in millimeter and the force unit are in Newton, so that's why its unit here in this case is Newton per millimeter. Okay. Now, G.
Sir, in actual practice, what this quantity shows?
In actual practice, this is a term which is used in the design of the connection of a built-up section. Okay, and in locating the, I've shown the two uses of this. So this is a term which you will have to calculate. Sometimes there is no physical existence of a term, so there is no physical. This is like this is similar term like the stress. Okay, stress is force per unit area, but this is for force per unit length. But it has certain application, and we'll talk about those application in our next example. Okay, so you will have to calculate these to design the connection between various parts of a beam. Okay, so this shear flow concept is used in the design and in the determination of the shear center. So these are the two uses. Okay, and we'll talk about these two uses in detail. Okay.
Yes, sir. And sir, the term sir shear is not a fixed quantity of a plane, or it varies, or in its also flow from one plane to another plane, or one length to another length.
The concept of flow, why the name flow is given to us, we'll talk about this. The concept of flow, why the name given flow to this. Okay, so we'll talk about this in the shear flow in thin section, because that there you will understand why the name flow is given to this one. But this is not the real flow, and the shear flow varies across the cross-section dimension. And since V varies along the length of the member, so there is a variation of the shear flow, not only along the length of the member, but across the section also. And we'll draw the stress distribution diagram in this example. So this is here you can see. So this is for a particular section. So if you are moving from one section to another section, since the value of V will be different, this is 100 kilonewton at that section. But if this value is variable along the length of the member, then each section will have its own stress variation diagram. Okay, each section of the beam along the length of the member. Okay, so here we got this one, and if you calculate, so this is at the top we have 0, and at the bottom just plug in the value of y in this expression, so 1843 Newton per square millimeter. Now for the web, so this is similar. Okay, we'll have to calculate the first moment of area. So this is same as the shear stress formulation. QZ is this one, so just plug in the value, so you will get this expression. And at different location, Q at top, at neutral axis, at bottom. Okay, so you will get at top 1839, 2030, and this is 0. Now here you will see a difference that at top of the flange, at top of the web, and bottom of the plane, which are same, so the shear flow is also same. Here you can see 1843 Newton and 1839, and this is just a rounding error 1843, 1843. Okay, so this is due to the rounding error, so they are having the same value. Okay, so here you can see and if you want to get the maximum shear flow, so you can use the maximum minima, and you know that the neutral axis, shear flow will be maximum. So this is the shear flow variation diagram. If you compare the shear flow variation diagram with the shear flow, the shear stress variation diagram, so the shear stress, there is an abrupt change at the junction of the web and flange. Okay, this is flange, this is web. So there is an abrupt change. But shear flow, the term shear flow, there is no abrupt change. It is because there is no B term in the shear flow. That abrupt change was due to B, because the width of the beam in the flange was 50 and width of the beam in the web was 10. But since there is no B terms in the shear flow, so this variation here is not, this abrupt variation here is not existing. So this is the variation diagram. Okay, so this is the shear flow variation diagram along the depth of the beam, and this is in Newton per square per millimeter. Newton per millimeter, these are the two values. Okay, now this is an example, a very simple example. After this example, you'll have to give me just 2-3 minutes just to have some water. So this is example 3.2. If the flange is connected to web through bolts, here you can see. Okay, this is flange, this is web. This is like this is a wooden plank whose cross section is this one, and its length may be equal to length of the beam. Okay, and this is another piece of wood whose cross section is this one, and in length will be equal to length of the beam. Okay, so these bolts will be applied through certain spacing. Okay, now these bolts will be applied at certain spacing, and it is required to know the spacing of these bolts, and the capacity of the single bolt is known to us. These are not the actual values, because 100 kilonewton capacity bolt, it's a very high strength bolt. Okay, so here you can see that this is the case, and this is in example 3.2. okay, in example 3.2 we calculated at the junction the shear flow is 1839 or 1843. Okay, so here 1843 is the shear flow at this location. Capacity of the single board is 100 Newton. Then what is shear flow is a force per unit length. Okay, so if you are applying boards at a certain spacing S, and the capacity of a single board is F, so the shear flow, if this force per spacing is equal to the shear flow, then this will be a like the capacity will be exactly equal to the demand. Okay, so Q is equal to F over S. F is the capacity of a single board, S is the spacing. Okay, since this is also force per unit length and this is also force per unit length. Okay, so spacing is equal to F divided by Q. F is 100,000 divided by 1843. So you will get 54.2 millimeter. Okay, 54.2 millimeter. So the spacing of this board should be like around about 2 inches. So you will have to apply the spacing at this. Now, since this 100 kilonewton may not be constant along length of the beam, which is usually variable, the shear is variable, and this spacing will also be variable along length of the beam. If you have a zero shear at a certain location, then you theoretically you do not need any bolt if you have a shear equal to 0. If shear is 0, then the shear flow is 0. Okay, there is no shear flow. Okay, practically you will need some bolts. Okay, some minimum spacing of the bolt, but theoretically they may not be required, and there might be certain location where the shear may have a higher value than this one, then the spacing of the bolt will be lesser than this value. Okay, so this spacing of the bolt depends upon the value of the shear. If the shear is variable, then spacing of the bolt will also be variable along length of the beam. Okay, but usually as a practical requirement, we apply certain spacing. We use if there is no requirement, but let's suppose I'm just supposing that if you are using a certain bolt, then let's suppose the value should not be equal, should not be less than 75 millimeter. If the design is giving you 100 millimeters, still you will have to apply 75. This may be the codal requirement. This may be the codal requirement, that this minimum, because you will have to satisfy not only this one, some other requirement also. Okay, because this is like, these are the spot values. Okay, you are not fully connecting this flange to the web. ये नुकसान है, स्पीकर बंद करें, स्पीकर बंद करें।
सर ये स्पेसिंग के बारे में पूछना था सर।
जी पूछें
सर ये स्पेसिंग सर ये 54.2 मिलीमीटर सर, ये स्पेस सर कहाँ स्पेस है सर?
ये देखें, मैं यहाँ पर इसको जो है वो, ये तो आपको क्रॉस सेक्शन नजर आ रहा है ना, ये एक बोल्ट लगा है, दिस इज लाइन ऑफ द बोल्ट, दूसरा इधर लगा होगा, तीसरा इधर लगा होगा, ये ऐसे जा रहा है, ठीक है। सो दिस स्पेसिंग इज एस, समझ गए ना इसको?
यस सर, बिल्कुल, थैंक यू सर।
अलोंग लेंथ ऑफ द मेंबर, ये तो आपको क्रॉस सेक्शन नजर आ रहा है ना, ये तो पूरे का पूरा बीम है। सो अलोंग लेंथ ऑफ द बीम यू विल हैव टू अप्लाई दिस स्पेसिंग, ठीक है?
ठीक है सर, बिल्कुल।
Okay. Now this is another example. So this is a modified form of the example given in the mechanics of solid by E.P. Popov. I've modified this a little bit. Okay, so in that example only he is talking about these bolt, but I've included this bolt also. He's talking about only these bolt, but I've included these also. These screws, these are not the bolt but screws. So a simple beam of 6 meter span carries a load of 3 kilonewton per meter, including its own weight. Let me draw that. This is a simply supported beam which is subjected to a 3 kilonewton per meter, 3 kilonewton per meter of load, okay, including its own weight. So here the reaction will be, since this is a 6 meter, total load is 3, 6 or 18, so this will be 9 kilonewton reaction, and here you will have another 9 kilonewton reaction. Okay, 9 kilonewton reaction. Okay, and if you draw the shear variation diagram, so 9, this is the shear variation diagram. Okay, shear variation diagram. I'll have to keep it or discard, so I cannot press it. Okay, so here in this case, this is a simply supported beam. Here at this support you have a 9 kilonewton shear, at this support you have a 9 kilonewton shear. So he is saying that specify the spacing of 10 millimeter leg screw shown to fasten the beam together at a section 1.5 meter from the support. Like from here up to here, this is 3 meters, the total is 6 meters. So he's saying 1.5 meter from the support at this center. Okay, at this center, at this location, this is 1.5 from the support. So what will be the shear value at this? This is 9, this is 0. So what will be the value at the center? 4.5. Okay, so he is saying that design it for here at this location. Also I'll have to discard it because I don't want to keep it here. So here the shear value is 4.5. Okay. So 10 millimeter screw, a capacity of single bolt is 1 kilonewton. Okay. He is saying that capacity of a single bolt is a single screw is 1 kilonewton. So the support reaction at the support is the reaction at the support. Support reaction at the support means support reaction. So at the support, let me remove this at the support. So the support reaction is 3 into 6 divided by 2. As I've told you, 9 kilonewton. The shear force at a section 1.5 meter from the support is 9 minus 3 into 1.5 is 4.5 kilonewton. Yani 4,500 Newton. The moment of inertia of this section. Okay, this is a section, so its moment of inertia is how much? I'm calculating the moment of inertia of this 2 times and this 4 times. Okay, so of this portion, which is 100 into 400 cube by 12 plus of this portion, which is 200 into 50 cube by 12 plus 200 into 50 into 225, this is from here up to here square, plus 4 times of this 50 into 100 cube by 12 plus 50 into 100 into 200 square. So this will give you the moment of inertia, which is 2.367 into 10 to the power 9 millimeter power fall. Okay. For shear flow at the junction of web and flange, I have this. So if I want to calculate shear flow at this location, so I'll have to calculate the first moment of area. As I've told you, if you want to calculate the shear flow at this location, then you'll have to calculate the first moment of area on one side of this one. So if you take a section here, so the one side is this one. Okay, so you will have to take the first moment of area of this shaded portion. So this is Q is equal to, so you have this one shaded portion, which is 200 into 50 into 225, and these shaded portion 2 into 50 into 100 into 200. So this will give you 4.25 into 10 to the power 6 millimeter cube. Now the shear flow at this location, VQ by IZ, so V is 4,500, Q is 4.25 into 10 to the power 6, and I is 2.36 into 10 to the power 9. So this will give you 8.08 Newton per square per millimeter. So this is the shear flow at this location. Now since the capacity of the screw is 1 kilonewton, okay, so spacing of the screws, what S is equal to the capacity F divided by Q, as we did in the previous example, this one. S is equal to F divided by Q. So S is equal to F divided by Q, and 1000 divided by 8.08 is 124 millimeters. So what should be the spacing of these screws? The spacing of these screws should be 124 millimeters into the center. Okay, but this is only where the shear is 45,000. Okay, since the shear force is variable along length of the beam, so these are applicable where the shear force is equal to or less than this value. If the shear force is greater than, then you will have to decrease the spacing. Okay, so if you are calculating the spacing exactly at the support, then you will have to double it, and since we will double, so this will be like 16 point something, and this spacing will decrease from 125 to 125 divided by 2, which is 62.5 or 62 millimeter. So it will reduce to 62 millimeter at the support, because at the support the value of the shear force is not 4,500, that is 9,000, double of this. Okay. Now for this screw, to design this screw, you will have to take a section here. Okay, so one side is this one, so just take the first moment of area of this shaded portion, so 50 into 100 into 200, so this is 1 into 10 to the power 6 millimeter cube. VQ by IZ is this one, so which is 1.9 Newton per square millimeter, and spacing of the screw is 1000 divided by 19. So 526 is a very high spacing. It may not be the practical spacing, but design requirement is this one. The strength requirement is this one, 526. You will have to at least, so these screws must be applied at a distance of 526. Okay, so these screws should be at a distance of what, 124 millimeter, and these should be at a distance of 526. Okay, so this is how to design the screws using the concept of the shear flow, the connection between various elements of a cross section using the concept of the shear flow. Okay, so just give me 2-3 minutes, so I'll have to continue this after 2-3 minutes. Okay. ओके जी, सो नेक्स्ट उसकी तरफ जो है वो जाते हैं शेयर फ्लो इन थिन सेक्शन की तरफ जो है वो जाते हैं। अब वो फ्लो का कॉन्सेप्ट जो है वो थोड़ा सा आपको जो है वो क्लियर हो जाएगा कि फ्लो का कॉन्सेप्ट जो है वो क्या है और वाई, मतलब वाई दिस इज नोन एज ए फ्लो। अच्छा, consider a thin wide flange section shown in the figure. It is required to calculate shear flow at a section in the flange at a distance A from the end. So I want to calculate, this is along the length of the beam. So I've taken a differential length. So this is dx, and this is a phi naught length. This is not a differential length, phi naught distance A from end of the flange. Okay, and I want to calculate the shear flow at this location. So here, this is in the cross section, this is a 3-dimensional view, and this is in the cross section. So I want to calculate the shear flow value at this location. Okay, the shear flow value. So the shear flow at this section can be calculated as Q is equal to dF by dx. And since this is what this is, a force, this is the shaded portion, so this is a force acting in this direction due to flexure. This is for acting in this direction, and there must be a force here. And if you just take the same measure, so you can get VQ by IZ. So definition is same, Okay. Now where Q is the first moment of area of this, similar to the shear stress. Now if you have a section here, and if you take a section here, okay, then you will get, let me just explain some more before discussing this one. Now this is a shear flow along length of the beam. This is along length of the beam. Okay, here this is a three-dimensional view. So you will get shear flow along length of the beam. Okay, so this is the shear flow. Now, as an equilibrium requirement, if you take an element here, like if you have taken element, if you take a point and just show as an element here, as a differential element here, then if you have a shear flow in this direction, then it must be accompanied by a shear flow in this direction. We calculated this one using this formula VQ by IZ, but similar to the case where we proved that the vertical shear stress is accompanied, or the horizontal shear stress is accompanied by the vertical shear stress. So this is the same case, that this shear flow is accompanied by this shear flow. Okay, if you have a horizontal element, then this is, if you take like an element here, then the shear flow will be in this direction, so you will have a shear flow in the vertical direction. But for the horizontal element, if you have a shear flow in this direction, that it must be accompanied by a shear flow in this direction. This is equilibrium requirement, so that you avoid twisting of this. So this is equilibrium requirement. So there will be a shear flow. You calculated from this the shear flow in this direction, but you got a shear flow as an equilibrium requirement in this direction, and I have shown it here, and I have shown it here also. Okay, so this is what this is, the shear flow direction in the flange. Similarly, if you take a section here and a section here and here, then the shear flow direction will be this one, here will be this one, and here will be this one. Okay, why the shear flow is in this direction and here in this direction? Because in the top, if you have compressive stresses, then in the bottom you will be having tensile stresses, and the direction of the force will get reversed. And if the direction of the horizontal flow is reversed, then the flow along the axis of the member reverse, then this flow will also reverse. So this is the direction of the shear flow. This is like this. This is in this direction. This is in this direction. And this is in this direction. Okay. Now, similarly, if you take a section here, then it will give you a shear flow along the axis of the member, and equilibrium requirement will give you a shear flow in this direction also. So in the web, the shear flow is in this direction. So now here you can see that this is what we are getting, the shear flow in the flanges and in the web. Now if you just look to this one, so this is like something is flowing. This is an analogy. Actually nothing is flowing in this one, but here you can see that something, that just like if you consider this as a pipe, so the fluid is flowing in this direction and this direction, then combining, flowing in this direction, then dividing in two parts, moving in this direction and in this direction. Okay, so this is not exactly, but this is like something is flowing through this cross section. Okay, something is flowing, and that's why the name flow is given to this one. Okay, that's why the name flow is given to this one. You will see that the shear flow will increase from here up to here. It will increase from here up to here. Then both of them will combine and flow in this one. So it will increase up to this point, then decreasing, and then dividing into two parts, and then moving like this. So this is similar to the shear flow. Actual values we will consider in our next example. Okay, so this is the concept, and this concept is also used in the design of the bolt, the design of the built up section, because the thin section, the steel sections are sometimes factory made built-in sections, sometimes they are built up section. Okay, you will have to join some plates to make these sections. Okay, so now coming to the shear flow variation diagram for the given section, V is equal to 10 kilonewton. This V could be any value along the length of the member. Okay, so this is an I section, this is a thin section. Now What is the definition of a thin section? The definition of a thin section that its thicknesses of the member are very small as compared to the overall dimension of the cross section. Now here you can see that the thickness is 10, overall depth is what? 400. So 410, 10 in 100 is 10%, 10 in 400 is 2.5%. So it's very small, very small. Okay, now 2.5% is ignorable value. This is ignorable value. Okay, so instead of specifying, instead of saying that the outer dimension is this one, so I'm saying that from center of this to the center of this is 400. Because if I'm saying that the outer one, if the center is 400, then the outer distance will be what? 410. So what is the difference between 400 and 410? Very small difference. So I can say that this is 400. Okay, so I'll be using this central line dimension in the case of thin section, because the central line dimension, and I'll be ignoring the some terms which I'll talk about, like in the case of the moment of inertia, I'm calculating the moment of inertia as sum of the moment of inertia of this web. I'm not taking the web as from here up to here. I'm taking that the web is 400. I'm taking the central line dimension 400. Okay, so 10 into 400 cube divided by 12 plus the moment of inertia of this flange and this flange. I'm ignoring the moment of inertia of this flange about its own centroid. Why? Because it is equal to 300 into 10 cube divided by 12, okay, which is almost equal to 300 into which is 300 into 12 cube. So its value is very small as compared to this value. It will be in thousands, but it is very small as compared to the millions. Okay, the value is in 1000, but it is very small as compared to the million. So if you just take, this is not the BD square terms of this one. This is the BD square terms, BD square, I'm sorry, AD square terms of this flanges. And I'm ignoring the moment of inertia of this flange about its own centroid, which is what? Which is 300 into 10 cube by 12. Okay. So this will simplify my calculation, and this will not produce a big error. It will produce just a 2-3% error, which is acceptable. Okay, 2-3% error in calculation is acceptable. Any design calculation is acceptable. Okay, so I'm using this one. You can calculate the exact moment of inertia. How? I'm calculating in my calculator. Okay, what will be the exact moment of inertia? I'm saying it like you have this bigger rectangle of dimension 300 into 410 cube divided by 12 minus these two spaces. Now the space is like, this is 300 minus 10, so 290 into what is the height. So if it is 400, then the height will be 390 of the space. So 390 cube divided by 12. So this is giving me divided by 289.5. This is giving me 289 or 290. Okay, and here from the approximated result, I'm getting a 293 value. The difference is just of 3 in 300. So this is 1%. Okay, or just above the 1%. So the error is not so much high. Okay, so I can use this. I can use the exact moment of inertia, or I can use this one. Okay, so this is something which I wanted to tell you. Just wait. Assalamu alaikum.
वालेकुम अस्सलाम
संगाले जी खैरियत ते जोड़े जी खैर दे
तो आप जी कहोगे
जी जी वाह
हमारा तो ये दुबई तक का मतलब कैसा है और जो मसला है ये चीज है तो Yung kuya na pagkarne, audio, nag-agree pa ni Marcia. Kaya mo siya.
او ملاو بشي دواړه سيزونه ملاو شي زه کور ته ټلیفون کوم ښه زه ورشه زه आप जरा वेट करें जी Okay, ji. So now this is the moment of inertia. Now the first moment of area, so to determine the shear flow in the flange, okay, shear flow in the flange. So let's take a section at a distance of x, okay, at a distance of x. So area of this shaded portion is 10 into x, and its centroidal distance is 200, so 10 into x into 200, so this is 2000 into x. Okay, x is a variable and it is varying from 0 to 150. I'm using the center line dimension, okay, from 0 to 150. Okay, so now this is the first moment of area. Now the shear flow is VQ by I. V is 10 kilonewton, and 10,000 divided multiplied by this divided by this. So this is 0.0682 x Newton per millimeter. So this is what this is the shear flow in flanges. Okay, so one thing here from this equation, it is clear that the shear flow varies linearly in flanges, horizontal element of the section, and it will always be the case that if you have a horizontal element, then the shear flow will vary linearly, like in this case. And if you have vertical element, then the shear flow will vary as a as a square of the variable. So it will be a 2-degree curve, and in the flanges it will be a single degree curve. Okay, so here you have this case. Now if you want to calculate the shear flow at this section, so you will have to plug in what, the x equal to 150. So if you plug in x equal to 150 in this expression, so 10.23, so the shear flow at this location will be 10.23, okay, in the flange. Okay, now similar, this is at this location, and similarly if you calculate shear flow from this plane, so it will also be 10.23, it will also be 10.23, and here it will also be 10.23. Okay, now for shear flow in the web, so for shear flow in the web, so I've taken the section here. So this is distance y, okay, and up to the center this is 200 plus y by 2 for this small portion, and this is the flange. So I've divided this into two, just like in the previous case. So Q is equal to, this is 3000 is this area, this is flange, into 200 is its centroidal distance, plus for this area, the area is 10 into 200 minus y. This from here up to here, this is 200 minus y. I'm using the center line dimension. I'm not saying that from here up to here, I'm saying that from here up to here. Okay, there will be a small error, but that is a negligible error. Okay, so 200 minus y, 200 plus y by 2. So this is 600,000 plus this one, simplify this, so 800,000 minus 5 square. Now the shear flow is VQ by I. Plug in the value, so you will get 27.27 minus 170.45 into 10 to the power minus 6 y square. Okay, so this is the shear flow variation diagram. If you plug in the value of what at this junction, so plug in the value y equal to what? Y equal to 200, because at this location, if you want to calculate in the web at this location, so this is 200. So 200, so this is 20.46, and at the neutral axis, Q is equal to 27, is y is equal to 0, so 27.27. Okay, so this is the diagram. In the flange you have 10.23, so I've shown it like this is the flow diagram. Flow is the flow is like in this direction, moving in this direction, and then in this direction. And it could be opposite. So this is for the case when you have an upward shear, because the shear flow will be opposite to the applied shear. Okay, so this should be in the upward direction. But if the applied shear is in the downward direction, then these arrows will get reversed. Okay, because the resistance is always opposite to the applied. Okay, for equilibrium. So this is the case. This is the shear flow. So this is, since the shear flow here is in this direction, here in this, so I've shown it like this, and this is in this direction. So this is the shear flow. Here is 10.23, 10.23, 10.23, 10.23, and here this is 20.46, 27.27, and 20.46. The one thing which, कोई question?
Yes sir.
जी पूछें.
सर आपने सर ये लोड कहाँ लगा है सर? इसमें तो लोड से मैंने नजर नहीं आता सर. आप सर अभी
लोड
बनाते हैं?
नहीं, लोड जो है वो शेयर लोड है. ये कहाँ लगा है वो एक अलग स्टोरी है, वो हम बात करेंगे. ठीक है, लेकिन लोड जो है वो एक वर्टिकल शेयर जो है वो लगा है, जो कि इस केस में जो है वो वर्टिकल शेयर इस केस में यहाँ लगा V. ठीक है ना, V. आई एम सॉरी, इसको मैं अगर रिवर्स कर लूं तो वो ऐसे है. V पॉजिटिव नेगेटिव दोनों हो सकता है, अपवर्ड भी हो सकता है, डाउनवर्ड भी हो सकता है. ठीक है ना, मतलब शेयर फोर्स जो है पॉजिटिव भी हो सकता है, नेगेटिव भी हो सकता है. सो ये वो V है जो यहाँ पर एक्ट कर रहा है.
सर शेयर तो पैरेलल नहीं होता है एक प्लेन के साथ. तो यहाँ सर आपने तो परपेंडिकुलर लगाया.
खुदा के बंदे. सो दिस फोर्स is not perpendicular, this is parallel to the cross section. आप अगर इस क्रॉस सेक्शन के देखें तो क्रॉस सेक्शन क्या पैरेलल नहीं है?
यस सर, ठीक है,
क्रॉस सेक्शन क्या पैरेलल है ना. ठीक है, आप तो क्रॉस सेक्शन को देखें ना, मैंने तो एलिमेंट के उसको नहीं दिखाया ना, क्रॉस सेक्शन के ये पैरेलल फोर्स है. ठीक है ना. अच्छा जी, तो ये हमारे पास अब इसमें कुछ चीजें नोट करने की है. वो नोट करने की चीज ये है, if you just combine this 10.23 plus 10.23, you will get 20.46. So what is happening actually? 10.23, 10.23 is 20.46. What is happening? That the shear flow is combining from this flange side and this flange side, 10.23 from this side, 10.23, and then they are combining to have a 20.46. If you add them up, you will get 20.46. Then it is increasing up to this one to 27.27. Then it is decreasing up to this point again to 20.46, and then dividing into two portions of 10.23, 10.23, and then finally getting to zero value at this one. Okay, so that's why the name flow is given to this one. Okay, the name flow is given to this one. So this is the shear flow diagram. Okay, this is the shear flow diagram. Now I want to let me show you the shear stress variation diagram, then I will come back to this one. Yeah, this is the shear stress variation diagram. Here you can see that the contribution here, this is a shear stress variation diagram. Okay, the contribution in resistance of the shear stress in resisting the shear stress by the web is very, very high as compared to the contribution of flange. Here you can see this is a very small contribution of flange. And here you can see a very big contribution of this web. Okay, so it is said that if you want to strengthen a beam in shear, then you will have to strengthen its web, because most of the shear force is resisted by the web. Most of the shear force is resisted by the web. And if you want to strengthen a beam in flexure, then you will have to strengthen its flanges, because if you have a stress variation diagram, flexure stress, let me draw the flexure stress variation diagram. So the flexure stress variation diagram is like this one. So most of the flexure stresses are in the outer region. So if you are having more areas in the outer region, if you are strengthening the flanges, because flanges are here, okay, so if you draw the flexure stress variation diagram, so this is the flexure, so you have flanges here, so most of the area is in the flanges. If you strengthen the flanges, then it will be strengthened in the flexure. Okay, so if you want to increase the movement capacity of a beam, then strengthen its flanges. If you want to increase the shear capacity of a beam, then strengthen its web. Okay, and in the case of thin section, we are saying that the 100% approximately all the stress is resisted by all the vertical force is resisted by the web. Since this is a thin section, here you can also see that the shear contribution of the web is very high. Okay, now if I integrate this shear flow, which is in the web, over the whole depth of the beam, I'll get a force, because shear flow is what? Force per unit length. So if I integrate it over the length, then I'll get a force. Okay, so this is a shear flow. So this is the length from here up to here. If I integrate it, I should get a certain force, and let's see what force I'm getting. So if I integrate this shear flow Q into dy from minus 200 to 200, because the total depth is 400, so here the value is minus 200, here the value is plus 200. So if I integrate it from this to this, so then plug in the value of Q, integrate it, plug in the limits, so you will get 10,000. What is this 10,000? This is the shear force. Okay, so when you integrate, so it means that the 100 in the case of thin section, you can say that the 100% shear is resisted by the web. Web ही उसको resist कर रहा है, ठीक है ना? The contribution in the case of thin section, the contribution of the flanges is zero, practically. Okay, theoretically there must be some values, but that will be ignorable value. Okay, so most of the are 100%. In the case of thin section, we can assume that 100% shear is resisted by, and since we are ignoring the effect of the thickness in this calculation, in all this calculation, so that's why I'm getting the exact 10,000 Newton force from this calculation. Okay, so this is a very important example where you will get the concept of the shear flow and the associated different conditions and different things, and certain factuals, certain facts to have will give you insight in the shear flow. Okay, now this was a shear flow in the thin section. So now coming to the shear flow in thin closed section. This is also a thin section, but thin closed section. Now, in the case of open section, when we just take a section where we want to calculate the shear flow, so we take area on one side of that. Like here, we take a section here, so we take this area. If we take a section here, then we take this area. What will be the case in the case of closed shape? If we take, let's suppose this is a closed shape, if we take a section here, then we take this area or this area, both will give you the same one. Okay, so in the case of closed section, there is something, say there is an additional thing which you should remember, that if you want to calculate a shear flow at this section, then you will have to take a symmetrically section on other side, and you will have to take another section, and you will have to then calculate the first moment of area between these two sections. Okay, and then calculate the first moment of area of this shaded portion, calculate the shear flow. But the shear flow at this location will be half of this, because this is shear flow is dividing into two parts. One shear flow is producing here and the other shear flow is producing here. So that's why you will have to divide it into two parts. Okay, so this is the procedure in the case of a closed section. In the case of closed section. Okay, so this is the case where the applied shear is 100 kilonewton, and this is the moment of inertia. So I'm two webs and two flanges. So 346.67 into 10 to the power 6 is the area. So to determine the shear flow, so I'll have to first in the flanges, I'm taking a segment at a distance of x from this center. So this is x. So I'll have to take on the other side also. So Q is equal to 10 into 2x into 200 is this one. So the shear flow is half of VQ by I. So this is the shear flow. So which is 0.07577x. So once again, you can see that the shear flow varies linearly because this is horizontal segment. And at this end, the shear flow is 8.65 Newton per, if you plug in x equal to 150, so that will give you 8.65 Newton per millimeter. Okay, at this location, at this location, at this location, at this location. Okay, now for shear flow in the web, if you are taking a section here, then you will have to take a symmetrical section here. So then you will have to calculate the first moment of area of this portion. Okay, so for shear flow in the web at a variable distance y from the neutral axis, so Q is equal to this one. This is for this portion, and plus 2 into 10 into 200 minus y, and 200 plus y by 2. So you will get finally 1000 minus 10 y square. Okay, so the shear flow is half of VQ by I. Plug in the value, you will get this expression. So the shear flow at y is equal to what? At y is equal to 200, meaning at this point. So this is 8.65 Newton per square millimeter. And the shear flow at the neutral axis, y is equal to 0, is 14.42 Newton per square millimeter. Okay, so this is what this is. You got various values of the shear flow, and these are the shear. This is the shear flow. Here you can see starting from 0. So this is like moving in this direction, then in the web reaching a maximum value, then decreasing, and reaching a 0 value. And same is for the other side also. Okay, so this is the shear flow maximum 8.65. Since this is only the shear flow is coming from only one side of the plane, so that's why it will start in the web. It will start at 8.65. Here is 8.65. Here is 8.65. Then increasing to 14.42. So the shear flow variation diagram for the section is shown in the figure. Note that the shear flow at the corner is the same for both flange and web. Also note that the shear flow is maximum at the neutral axis. So, but I've told you that this should not always be the case. Okay, sometimes shear flow is maximum not at the neutral axis, at some other location, just like in the case of a triangular section. Okay, now coming to another concept of the shear center. So I think let's have a break of 20 minutes, and then we will continue the shear center, and then we'll complete it. Okay, we'll try to complete it before 11 o'clock. So just if you have any question, you can ask. Otherwise, let's have a break of 20 minutes.
सर वो पॉइंट दोबारा रिपीट कर। सर आपने कहा कि वो जब आप स्ट्रेंथन वेब को स्ट्रेंथन करोगे तो क्या होगा, और फिर फ्लिंजेस को स्ट्रेंथन करोगे तो फिर क्या होगा? आपने कुछ बोला लेकिन वो क्लियर नहीं होगा हमें।
देखें, मेरे पास ये section है ना, let's suppose this is section, okay? If I draw the flexure stress diagram for this, let's draw the flexure diagram for this, okay? The flexure stresses diagram for this. Let's suppose one is tension, the other one is compression. Okay, you have maximum value at top and bottom. Okay, at top and bottom you have maximum value. Okay, now you can, here in the case of shear, let's suppose if I'm increasing web, strengthen web mean increase the thickness of the web. So if I'm increasing thickness of the web, what will I get? I will get increase in the resistance of this web. This will, the stresses developed will be lesser if I increase the thickness. And since this is a material which has some shear strength, strength has nothing to do with the dimension. Okay, like the shear strength, let's suppose the shear strength of a steel, let's suppose is equal to 30 ksi. Okay, so this is the strength. So if you are increasing the thickness of these, so what will happen? The shear flow will the shear stresses will get decreased. Okay, the shear stresses will get decreased, and that is good for what? That is good for the shear. Okay, so if you increase this, so if the shear stresses are get decreased and the shear strength is high, so this is good. Strength is high and stress is the demand. So your capacity is higher and your demand is less. But if you are making it thinner, so what will happen? Stresses will get increased. And if the stresses are getting increased, then what will happen? Then it may reach the strength of the material, and that will cause a failure of the thing. Okay, so if it is said that if you want to strengthen a beam in shear, then strengthen its web. Strengthen mean increase its size, increase its thickness. But if you want to strengthen a beam in flexure, then increase the thickness of the flanges. Okay, so how to increase thickness? If you have an existing beam, how to increase the thickness? So you will have to weld an additional plate to the flanges. Like you can have a plate like this. I'm sorry. I can have a plate like this. Okay, just weld this plate, I'll bolt it. So this is strengthening of the flanges. Okay, what will happen in this case? Since there are more stresses here, and if you are having more area in this region, so it will do what? It will strengthen this case. Stresses, since the stresses are maximum here, so the capacity will also get increased. The flexure formula is saying that stress is equal to M over S, or My over I, or this is stress is equal to M over S. S is the section modulus, you know this. Okay, so if you are strengthening this web, as well increased. Okay, the section modulus will get increased if you are increasing the area of these flanges. Okay, so this is the reason why we are saying that if you want to get strengthen as something in flexure, then strengthen its web. But sometimes you will have to increase both of the shear, and then you will have to then strengthen if let's suppose if it is required that you may require that strengthen the beam in flexure as well as in shear, then you will have to obviously increase both of them. Okay, but if it is okay in flexure but weaker in shear, then you will have to just don't touch the other segment, just increase the web thickness, or just weld a plate on to the web on both sides. Like you can have plate here, you can have plate here in the deficient region. ओके, बस सिर्फ जहाँ पर शेयर ज़्यादा है वहाँ पर जो है वो उसको वेल्ड कर ले उसके साथ, सो इट विल बी ओके। ओके
यस सर।
ओके जनाब, चलो जी। सो हम मिलते हैं 20 मिनट में, ठीक है?
इंशाल्लाह। Hello,
Hello.
Abdul Nasser.
Yes, Abdullah.
The break time is not over.
I don't know. Yeah, I think it was 20 minutes. Now it's about 10 minutes. It is that.
That was 20 minutes, but it's 10:30 here.
Let's put the tick.
Ijaz sir is in class or not?
जी जी।
Sir, ये class.
बस सर का कोई काम होगा ना, आप वेट करें थोड़ा।
ठीक है सर, शुक्रिया सर।
अस्सलाम वालेकुम, आवाज़ आ रही है मेरी आपको?
Walaikum salam. Yes, sir, your voice clear.
ओके, अच्छा चलो, शेयर सेंटर जो है वो, लेट्स डिस्कस द शेयर सेंटर. सो फर्स्ट आई एम गोइंग टू डिफाइन व्हाट इज शेयर सेंटर. Shear center is a point such that if the shear force applied on the section passes through this section, twisting moment will not produce in the section. It is a point, and what is the source of twisting? We'll talk about this one in detail, but you will have to apply your shear force. Your shear force should pass through the shear center, not through the centroid of the cross section. It should pass through the shear center. And if it is passing through the shear center, the section will not twist. It will just bend, shear forces will be induced, but there will be no twisting moment induced in the section. But if the load is not passing through the shear center, then what will happen? The section will twist. And in addition to the usual shear stresses, due to the twisting or the torque, some twisting or shear stresses, additional shear stresses will also be induced in the section. And if your load is not passing through the shear center, then you'll have to take care of those stresses when you are designing. Or if you want to avoid those stresses, then you'll have to pass your load, you'll have to make some arrangement that your shear force should pass through the shear center of the section. Okay. Now, what is the source of that twisting? So let's talk about this. So for that, so consider a channel section. So this is a C channel section. And in this channel section, the depth of the channel section is H, the width of flange is B, thickness of the flange is TF. Okay. And moment of inertia of this channel section is supposed to be I. Okay. Now the shear flow in flanges, the shear flow at this location at the end of the flange will be what you will have to take this area in calculating the Q. So by definition, QF is equal to VQF by I. So this is V over I. QF is area of the flange, which is BTF, into the centroidal distance, which is from here up to here. This is H by 2. So BTF into H by 2. So if you simplify this, so shear flow in the flange at the junction of the web and flange is like this value is VBHTF divided by 2I. Okay. Now, since I want to calculate the force in this flange, because this is the shear flow direction, shear flow is moving like this. So this is the shear flow. So if you just integrate the shear flow, you will get a shear force. In this case, since the variation is linear, so there is no need of integration. You can very easily get the average value of the shear flow. So the average value is here you have a 0 value, here you have this value. So QF plus 0 divided by 2 is equal to VBHTF divided by 4I. So this is the average value. Okay, average shear flow in this flange. How to get the force in the flange? This FF. So FF is the average into width of the flange and the length. Okay, so this is equal to VB square H TF divided by 4EI. So this is force in flange. Now in the web, in the top flange, the force is like this, and in the bottom the force is like this. Okay, this is according to the shear flow. This is according to the shear flow definition. Okay, and the shear flow in the web is like this. Okay, the shear flow in the web is like this. So if you integrate it, so we know, just like we did in the previous example, that if we integrate the shear flow in the web, we get the shear force. Okay, the actual applied shear force. So this will be equal to V, the applied shear. Okay, the applied shear. Okay, now let's talk about this one, this FF. So now if we reverse, this is the applied shear. Okay, this is applied shear is applied here. So if you reverse the applied shear, then these arrows will get reversed. It will be like this, then this direction. Okay, so it is making no difference. Okay, so just the direction will get reversed. Now if you just see these two forces, so they are making a couple. Okay, this FF in the top and in the bottom flanges, they are making a couple. And this couple is, in this particular case, is a counterclockwise couple. So it is trying to twist the section, because this is an axis passing through perpendicular of this point is the axis of the member. Okay, so this is causing to twist the member. Like this is member. I show it in this direction. This is member, so this is axing, so the torque is applied in this direction, so this is trying to twist this member. Okay, this couple is trying to twist the member. Now you will have to, this is the source of twisting in this particular case. The source is what? Forces in the flanges because of the shear flow. Forces in the flanges because of the shear flow. Now you will have to, now this is the case, now you'll have to apply your shear at a certain location that it counterbalance this couple. Okay. Now if I'm applying, let's suppose this is producing a counterclockwise couple, so if my applied shear is passing through this point. Okay, this is my applied shear, which is at a distance of E from the center of the web. Okay, so this V and V, this is resistance and this is the applied shear. They are also creating a couple, and this couple is a clockwise couple. It should be. If I'm applying my force here, then it will produce a counterclockwise couple, which will reinforce this couple, which is not desirable. I want to cancel the effect of this couple, so that's why I'll have to apply my shear force at this location, okay, at a distance of E, so that the couple produced by this one is in opposite direction to this one. So to avoid twisting, just a minute. Hello? So 15 minutes के बाद class खत्म, 15-20 minutes. Okay. So this is the twisting couple, okay, and to resist this, so this couple V into E must be equal to this twisting couple. Okay, so if they are equal, then there will be no twisting. Okay, this is producing a couple in a clockwise direction, and this FF is producing couple in the counterclockwise direction. So if they are balancing each other, then there will be no twisting. So V into E must equal to this. So E is equal to this one. So E, this is the right hand side of this is whole geometry. V is geometry, H is geometry, TF is geometry, I is geometry. These are geometry dependent terms. So E, you will get a value, okay, of E. Okay, E is the distance, this distance. So let's suppose you are getting a 3-inch distance. Okay, so you will have to make certain arrangement while applying the applied shear to this channel section, that you will have to, let's suppose a concentrated load is applied. So you will have to weld a plate, and the line of action of the shear force should pass through. Because since this is what the application point, or the application line of this load is outside the cross section. Okay, outside the cross section. So basically, this is what, if I extend this line, so this is the shear center. This point is the shear center. Okay, and its value is equal to this one for this particular case. Each case will have different shear center values. Okay, so this is what, if you are applying, so you will have to, how to apply, how to pass your shear force to this point. So this is what you can have a plate welded here, and you can apply the force at this location. Otherwise, you will have to design it. If practically it is not possible to apply, to weld a plate to this and to apply, to pass the shear force to this point, so then in that case, you will have to then design it, okay, for the additional stresses.
Now, one thing for the shear center is that shear center always lie on the axis of symmetry. In this case, this horizontal axis is the axis of symmetry. Shear center always lie on the axis of symmetry. So for symmetric section, doubly symmetric section, since the centroid also lies on the axis of symmetry. Okay, so for doubly symmetric section, the shear center and the the centroid coincide with each other. Okay, but for monosymmetric section, like this is a monosymmetric section. This is about symmetric about this one, but not symmetric about this one. So this is the axis of symmetry. So the shear center will lie on this one, but not on the other axis. It will be off. So for a channel section, the shear center is always at the base of the web. Okay, at the base of web. And what should be this distance? If you plug in the value, let's suppose you are getting 3 inches, so you will have to this distance will be 3 inches. Okay, E is equal to 3 inches. Now let's have an example. This is example 3.7. Draw shear flow diagram of the given section and locate its shear center. The applied shear is B. Okay, so this is a section. So first you will have to calculate the moment of inertia. I'm not going into the detail of this. The shear flow is like in the two web, there is no shear flow in this middle portion. Why? Because if you take a section here and if you calculate the first moment of area of one side, so you will get 0, because it's centroid, the whole area lies at the centroid. So if there is no centroidal distance, so you will get 0. So the shear flow, there is no shear flow. The shear flow is in this one as in this one. This portion is not taking part in the shear resistance. Okay, so this is the shear flow. So how to get the shear flow? So the first part is just to draw the shear flow diagram. So just take a section at a distance of y, and for the left side, this is the first moment of area, and this is the shear flow variation diagram. And if you just calculate at the neutral axis, so that the neutral axis, the shear flow is equal to this one. So this is the shear flow diagram. This is neutral axis is 1111. So this is in Newton per meter times V. 1111 times V. V is the applied shear. He is saying that the applied shear is V. Okay, into 10 to the power minus 6 V. This is shear flow. Now the shear flow for the right segment, similarly, you can take a segment, and first moment of area of this is equal to this one, and then calculate the shear flow in the right segment. So at the neutral axis, so this is 4444 into 10 to the power minus 6 V. So this is 4444. So this is the shear flow variation diagram for the right segment. Okay. Now, if you integrate this shear flow, you will get a force in this, which is VL. And if you integrate this one, you will get a force, which is VR. VL is the vertical force in the left vertical segment, and VR is the vertical force in the right vertical segment. So if I integrate the shear flow, this shear flow, so VL is Q, I'm sorry, this is VL. So if I integrate this VL into dy, so this is VL into dy, so I'll get integration from minus 0.75 to 0.75. Okay, so I'll get 0.111 V. And if I integrate VR, this one, from minus 150 to 150, I'll get 0.889 V. If I add them up, I should get V. Why? Because the vertical shear is resisted by this and this. So some of them should be equal to V. And this is, I'm getting V. Okay, so note that V is equal to VL plus VR. Now there is no need, if one is known to you, then if let's suppose VL is known to you, VR is very easy. V minus VL, you will get VR. So there is no need to calculate the other one. So that's, I wanted just to show that it is equal. So that's why I did calculation for both of them. Otherwise, there is no need of them. Now taking moment about the left hand. So if I take a moment about the left hand, so this is the applied shear, okay, which is at a distance of E from this. So V into E must equal to VR into 400. So V into E must equal to VR into 400. This is the equilibrium requirement if there is no twisting. If there is no twisting induced in this section, then if this is the shear center, then V into E must equal to this one. So E is equal to 356. So the shear center is located at a distance of 356 from the left hand, and 44, if you just 100 minus 356 is 44. So this is at a distance of 44 from the right hand. So this is the shear center. So your load should pass through the shear center. So this is the axis of symmetry. Okay, this is the axis of symmetry. So it should lie on this axis, but this one, this is not the axis of symmetry, so it must be passing through this point. So you can see this is the centroid and this is the shear center. Okay. Now let's talk about, this is the last example of today's lecture. So example 3.8. Draw shear flow variation diagram and locate shear center for the split tube. This is a split tube. You take a sheet and make a shape of like you take a piece of paper and rolled it like this one. So this is a kind of a split tube. Okay, but this connection is not welded to each other. They are not joined together. So if you join them through some bolt, some welding, then this is not a split tube. Okay, this is a closed tube then. Okay, so for split tube of radius r and thickness t as shown in the figure, the vertical shear is, so we'll have to draw the shear force variation diagram and locate the shear center for this one. Okay. So consider a differential element at an angle of theta, making a differential angle d theta at the center of tube. So this is like a differential element at an angle of theta, and this is differential element is making an angle of d theta differential angle at the center of tube. So this will be equal to r d theta. The length of this element, this differential element, will be r d theta. And what will be its area? R t d theta. Because thickness of the tube is t, so r t d theta. So I is equal to y squared dA, and this is y. This is the neutral axis, and this is y. Y is from this operation. This is r. This is theta. So y is equal to r sine theta. So y square, as per definition of I z, is equal to y squared dA. So I is calculated for the whole cross section. For this whole cross section. So I is equal to r cube t divided by, from 0 to 2 pi, y square, y is r sine theta square, and d is r t d theta. So if and integration is from 0 to 2 pi, from here to this whole cross section, because I is calculated for the whole cross section. So if you integrate this, I'm not going into the details, so you will get pi r cube t. Pi r cube t is the moment of inertia of this thin tube, a thin split tube. Okay. Now to calculate shear flow at an angle of alpha, let's suppose I want to calculate a shear flow here. So what is the procedure? I'll have to take the first moment of area at one side. So this is one side. Okay, so I'll have to calculate the first moment of area of this shaded portion. How to get this? So if I take the same differential element and integrate it from 0 to alpha, I'll get the first moment of area. So Q is equal to y dA, y is r sine theta. So this is integration from 0 to alpha. Okay, so simplify this. So r square t into 1 minus cos alpha. Okay, so this is the first moment of area. And then the shear flow, Q is equal to VQ by I. V is this one, Q from the previous slide. So this one, I pi r cube t. So this is V into 1 minus cos alpha divided by pi r. Okay. So this is the shear flow variation diagram in terms of alpha, because this is a circular section. So in the case of circular section, so you can have the value of alpha. Alpha is an angle starting with the split. Okay, now this alpha is the angle starting from the split. Okay, so at alpha is equal to 0, Q is equal to 0. This pink color is the variation diagram for the shear flow. So at this, there is no shear flow. At alpha is equal to pi by 2, Q is equal to V by pi r. This is the shear flow. At alpha is equal to pi, so this is 2V divided by pi r. at alpha is equal to 3 pi by 2. So this is once again V by pi r, and alpha is equal to 2 pi. So this is once again 0. So starting from 0 and then developing and then ending with the 0 one. Okay, so this is the shear flow direction like this. Okay, starting from here 0 value and then increasing up to this, then decreasing and ending with a 0 value. Now if you look to this, so this is the shear flow, these arrows are the shear flow, and this is the shear flow diagram. Okay, now if you look to this one, okay, this shear flow is trying to induce a twisting moment in the section. Okay, a twisting moment in the section. Now how to get this twisting moment, because the shear flow is not uniform. So once again I am taking a differential element at an angle of alpha, which is making a d alpha angle, so its length is r d alpha. So the df force is equal to what? Df is equal to q into r d alpha. This is a df force, and df is having a momentum of r. So df into r is the torque. If you integrate it, so you will get the total torque. So df is equal to q r d alpha into r. Now you integrate it from 0 because you want to calculate the total torque from 0 to 2 pi. Plug in the value, finally you will get 2VR. So this is the total torque which is produced due to this shear flow. Now let's suppose the applied shear is passing to this one, because since this is a counterclockwise torque, okay, so the applied should be a clockwise torque. Okay, so if the applied is a counterclockwise, then it should be clockwise. Okay, so if this is E, so V into E is equal to T. Okay, this if you take a moment about this one, so this is producing a clockwise and this is counterclockwise, both of them should be equal. So V into E is equal to T. So VE is equal to 2VR, so E is equal to 2R. So the shear center for this split tube is at here. Okay, the split tube is here. So this is the shear center location. So we draw the shear flow diagram and we locate the shear center. You can do a very simple experiment. You can take a steel sheet, okay, and rolled it to make a tube, okay, and then apply and don't connect them to each other, so it will be a split tube. And if you place the split tube in this portion, in this situation, if you apply a load in this direction, just press it. So what you will observe that it will roll. Because of the twisting movement, it will roll. Okay, it will roll because the shear center is here. You will have to apply a load here. Okay, you will have to make some arrangement to apply the load here. Okay, just a minute. Hello. Walaikum salam. जी डॉक्टर खैर लगा
सर मतलब ये तुम सेलो जेम्स की हवा चिकन ना हो बना वॉलपेपर ही रहेगा ऑलमोस्ट कंप्लीट मैं तो बच्चा मेरे कर रही
बस माता पिक्चर रावलेगा माना बस विजिट को बस ठीक देखना यार ठीक माता पिक्चर रावलेगा बस ठीक तो सही रहा ठीक. So now if you just have some hoops उन दोनों के ऊपर जो है वो कुछ आप उस ट्यूब के ऊपर कुछ जो है वो कुछ धागे से उसको बांध दे, उसके ऊपर जो है वो चढ़ा दे, तो वो स्प्लिट ट्यूब पे नहीं रहेगा क्योंकि उसमें रेजिस्टेंस जो है वो आ जाएगी. Now if you apply a load at this location, then you will see it will not roll. ठीक है ना. Without that connection with the split, it will roll because of the twisting movement, but it will roll like this. Okay, but if you just have some hoops here, you can कुछ धागे वगैरह उधर बांध दे, then it will not roll. So this is a simple experiment. Okay, so this is the end of today's lecture. If you have any question, you can ask.
No, sir.
Okay, thank you. चलो जी, रिकॉर्डिंग स्टॉप करें.